Finally, let's look at one more example of real life heavy atom tunneling. In this case of Y2C2 at C92, where C92 is a fullerene cage, a carbon cage, um, with 92 carbon atoms, and inside of it two yttrium atoms. I'll explain why we show more than that here in a moment. And then inside also a pair of carbon atoms called a carbide group. The gadolinium version of this molecule was characterized by a research group at University of California, run by Alan Balch, um, by X-ray diffraction. And so what he found is that there was a fair amount of movement in the yttrium atoms. He could X-ray the yttrium atoms in several different places, but that the carbide group, according to his X-ray data, sat fairly still, and that the most likely positions for the gadolinium atoms were at 90 degrees and in plane with the carbide group. Now, we can't get decent NMR data on the GAD version of this because the unpaired electrons on gadolinium um, interfere with the magnet, and so we can't get a good NMR spectrum. But when a group at Virginia Tech isolated the yttrium version of this molecule, we were able to get good NMR data. And the NMR that we gathered suggested that we should have the same structure that Alan Balch found, that is this cross, this T-shaped structure to the internal cluster. But when we performed molecular modeling calculations on this, we found that the lowest energy configuration was not a perfect cross, but the carbide tilted and out of plane from the yttrium. And so this was unexpected, and we ran the calculation several different times with several different starting geometries and found that, and which makes the yttriums and the carbons somewhat unequivalent in the or should have in the and change the should have changed the splitting of the carbons due to the yttriums by breaking that symmetry, but it did not, or at least it didn't visibly to us at first. So we reran these several times, and what we found is that the expected structure based on the NMR and based on Alan Balch's X-ray of the gadolinium version is not the optimized structure, but it's a transition state between two optimized structures with a energy difference between the transition state and the optimized structure that's fairly small, 3 kilocalories per mole. And whenever we optimize and find a transition state structure, we get an imaginary vibrational frequency that corresponds to vibrating through the transition state structure between two optimized structures. And here's a video of what that vibrational state looked like. So this is exactly what we expected, and so the idea here was that the carbon is vibrating so quickly between those two states because it's such a small energy difference, 3 kcals per mole. It's vibrating so quickly between those two states that the NMR sees the average instead of seeing one state or the other. So we went back to the NMR and ran this on a very high field NMR with lots and lots of scans. Ran for over a month on an 800 megahertz NMR. And what we found was that some of the atoms around the cage, around the equator, around where the carbide carbons would have been close to if it were rotating inside the cage, were broadened. And we would only expect that if the carbide group was rotating through there, because the carbide would have a negative charge to it. It's a C2 minus ion, and so that negative charge rotating past each of those carbons would broaden their peaks in the NMR. So this only became visible at very high field with lots and lots of scans, and it was Hollings Marine Laboratory NMR that made these scans for us. So we went back to the drawing board a little bit and started to calculate an actual path between the two optimized structures through the transition state. It was such a large calculation we couldn't get it to complete, but we got it to go far enough to show that the NMR data was borne out by computation, that what we have is internal rotation and vibration going on at the same time. Now, none of this has implicated tunneling in any way yet. But let's look at the data a little bit further. Here's a plot of position of rotation of the carbide group, starting with a transition state structure and then moving down in energy to one of the optimized structures, rotating further to another transition state after 60 degrees of rotation, and then after 100 degrees of rotation, 180 degrees of rotation, we would have an equivalent structure to the first one because of the symmetry of the C2 group. Now here's where the data started to get a little bit weird. If we treat that internal carbide group as a free rigid rotor with no rotational barriers on it, we should expect to see in the Raman spectra certain Raman shifts, certain peaks, and we see those peaks almost exactly. We should not see those peaks if there is a rotational barrier. But we just calculated a rotational barrier of 3 kcals per mole. That should have been large enough to obscure those peaks from being visible in the Raman spectrum. However, the peaks were there and were approximately where we expected them to be. So how is this happening? The only way that we could suggest that this is happening is that the carbon atoms are actually tunneling through that rotational barrier. And again, we'd have a much larger mass here than we expected, and we could have the potential energy right here and then calculate the probability of that tunneling happening. But this was the only explanation we could come up with, and this was the explanation that we published in Physics Review B a couple of years ago.